everyone. Today we are going to study about the blackbody radiation. In the previous lecture, we have studied about the origin of quantum mechanics and the Planck's law and the subsequent discoveries by other scientists to explain various phenomena which cannot be explained using classical theory. So today the topic of discussion is black body radiation. So what is black body radiation? In order to understand this, first we must know what is black body. So a black body is a body which can absorb all the radiation incident on it. So a black body is a body which can absorb all the radiation incident on it. When a body is heated and when it comes in thermal equilibrium with the surrounding, it emits radiation. When that body is absorb light, more and more it absorb light, more it can emit the radiation. So if a body like a black body absorb all the radiation incident on it, when it comes in thermal equilibrium with the surrounding, it can emit all the radiation it absorbed. So a black body is a perfect emitter as well as a perfect absorber. So a black body can absorb the radiation, means 100% absorbance. It's a perfect absorber as well as a perfect emitter. What is black body? So this is the definition of the black body. Now what is black body radiation? The radiation emitted by a black body is known as black body radiation. We must know that in order to study about the black body radiation, we must have the subject. So if we have we want the subject like black body, which is available in the universe, like black holes. But black holes are far away from the earth, and it is difficult to study over the black holes because they absorb all the radiation coming near to them. So scientists thought to make a practical black body. A practical black body, how can we construct a practical black body? So practical black body can be constructed by taking a hollow sphere and making a hole over it. So if we see the cross section of the black body, it appears like this. We are making a small hole over it. This is the hollow part and this is the solid part. We are notifying it with the lines. Solid part. Here a bulging can be made which does not allow the radiation entering into the cavity to get reflect back. For example, the radiation entering this way is strike over here, then it does not get reflect back in the same direction because it is having some angle. Now it travels there, now it travels there. So the direction of the changes and it gets trapped, or the radiation changes and it gets trapped inside the cavity. It cannot escape out from that hollow cavity. So it works as a practical black body. So if we study the practical black body radiation spectrum, so the radiation interaction with matter is important. So when a matter is heated, then it glows and it emits thermal radiation, and its color changes from red to yellow and then to white. So there is a continuous distribution of frequency changing from infrared to ultraviolet. So if we plot the spectral energy density with frequency, we get a continuous distribution curve like this, U, nu, T, and here nu is the frequency, U is the spectral energy density, and this is for T equals to 2000 Kelvin. We get a continuous curve for the spectral energy density with varying frequency at a temperature T. But previously it was known that when the emitted gas heated emitted gas have discrete absorption lines. So this is discrepancy, and to explain this, various scientists have proposed various laws and have tried to explain the phenomena behind this, and why we are getting the continuous distribution. So one of the scientists, Stephen Boltzmann law, find out the power radiated per unit surface area, or we can say the intensity. He find out, according to Stephen Boltzmann law, he find out experimentally that P is equals to sigma A T to the power 4, where P is the power radiated per unit surface area, and sigma or you can say the intensity, P is the intensity, and sigma is the Stephen's constant, and experimentally its value is about 5.67 into 10 raised to the power minus 8 watt meter minus 2 Kelvin minus 4, and T is the temperature and A is the coefficient. And its value is less than equal to 1. For black body it is equals to 1. For black body this is equal to 1. A is equals to 1. So this is the Stephen-Boltzmann law, and T is the temperature in Kelvin. Later on, from this law, Wiens tried to find out the energy density per unit frequency per unit area, that is U nu T. So according to Wiens law, the spectral energy density denoted by U nu T is equals to A nu Q e to the power minus beta nu by T, where nu is the frequency, A and B are the parameters, and T is the temperature. There is also, we can find that this Wiens law satisfies the condition only at the higher, means satisfies the spectrum only at the higher frequency range. This and so this completely does not define the blackbody radiation. This is the graph between spectral energy density and frequency. We can see that the Wiens law can be satisfied only at the higher frequency range. So later on, Rayleigh also discussed and given a law to explain the blackbody radiation law. Rayleigh-Jean's law. This is called Rayleigh-Jean's law. So according to, he took the number of radiation, also number of modes in the frequency range in three dimension is 8 pi nu square upon CQ. So, and he took the average energy using the classical partition theorem, 0 to infinity e to the power minus e by kt dE upon 0 to infinity e to the power minus e by kt dE. So on solving this integral, we get equals to kt. So the total energy he find out, total energy u ut find out by multiplying the number of modes and the average energy of the oscillator. This is the total energy of the electromagnetic radiation inside the cavity, or also called as spectral energy density. So the total energy density according to Rayleigh law comes like this. This is the total energy density. But this formula, this law, Rayleigh-Jean's law, satisfies only at the lower frequency range of the black body spectrum, and it diverges at high frequency range. So later on, Planck's given a law called as Planck's distribution law. So first we make here we can show that if the we can show here Rayleigh law satisfied at the lower frequency. This is according to Rayleigh law, this is according to Wien's law. If u nu t and nu, okay, this is according to Rayleigh-Jean's law and this is according to Rayleigh-Jean's law. Now later on, Planck find out the law to explain the black body radiation. So according to Planck, the energy is quantized, that the exchange of radiation with matter, that energy is quantized, that the energy exchange between radiation and matter is quantized. So he took that according to, we are going to derive the Planck's distribution law. Okay, it's going to end. Planck's distribution law. So according to this law, he took that energy is not continuous, energy is quantized, that the interaction of and exchange of energy of radiation with matter is quantized, is discrete, where n can vary from 0, 1, 2, 3, and h is the Planck's constant and nu is the frequency. This is E is the energy of the electromagnetic radiation, and if we are considering a cavity, we can say that E is the energy emitted by the cavity, or E is the energy of the charge carriers inside the cavity. Means E represents the energy of exchange between radiation with matter. Now in the previous expression, we have seen that Rayleigh have considered that the electromagnetic radiation as the standing waves, and these are the harmonic oscillator, means they are doing the harmonic oscillation inside the cavity. But he did not consider that the energy is discrete, and he did not consider that every oscillator can have different frequency, but Planck considered that every oscillator can have different frequency. So he replaced the integration term with the summation term and he varies n. So by considering that the every oscillator can have different frequency, they can oscillate at different frequency, it is not necessary that they can oscillate, all of harmonic oscillator can oscillate with the same frequency. So he find out the average energy using the expression and replacing the integration with the summation by, and E in place of E you can write nh nu e to the power minus nh nu by kT divided by n equals to 0 to infinity e to the power minus nh nu by kT. We know that the expression n equals to 0 to infinity and x, these are some identities, x1 upon 1 minus x square, and n is equals to 0 to infinity x to the power n 1 upon 1 minus x. Taking the ratio of these two is dividing, if we are dividing both of them, that is n equals to 0 to infinity n x n upon n is equals to 0 to infinity x to the power n is equals to x upon 1 minus x. If we consider here x as e to the power minus h nu by kT, so we can write here as x is n equals to 0 to infinity and h nu is not varying with n, we can take it outside, and this quantity is x to the power n, x n is equals to 0 to infinity x to the power n. So h nu, this ratio we have found out here, and it is h nu x upon 1 minus x. What is x? H nu e to the power minus h nu by kT upon 1 minus e to the power minus h nu by kT. So if we multiply it with e to the power plus h nu by kT in the numerator as well as in the denominator, this power become 1. So we have to multiply here both e to the power h nu by kT upon e to the power h nu by kT. So this becomes h nu upon e to the power h nu by kT minus 1. So this is the average energy of the harmonic oscillator, or the average energy of the electromagnetic radiation. This is the average energy. Now we can find out the total energy of the harmonic oscillator, total energy of the electromagnetic radiation, called as spectral energy density. We know here the average energy. So total energy is we representing here u du t. Mode is in 3 dimension. If we are taking 3 dimension, c cube h nu e to the power h nu by kT minus 1. So this is the Planck's distribution law for the spectral energy density. Now we can see that from this law, both Wien's law as well as Rayleigh's law as well as Stephen's law can be derived. It's a complete law explain the blackbody radiation spectrum. So it explains the blackbody radiation. So if we take the frequency is very high, nu is very high, very high, frequency is high, then this 1 can be neglected in comparison to 1, in comparison to this factor. the u nu t is equals to 8 pi nu square upon c cube h nu. This can be neglected. So we get e to the power h nu by kt. It is equals to 8 pi nu square upon c cube. This can be written as h nu cube e to the power h nu by kt. Okay. So this if we take it above, it becomes e to the power minus h nu by kt. So previously we have written a nu cube e to the power minus beta by t. So a and beta are here these parameter. A is equals to 8 pi h upon c cube and beta is h upon k. Beta nu by t. Beta nu by t. This is beta nu by t. So now this from this law, when frequency is very high, means law can be derived, and when the frequency is very low, u is very low, u nu t is equals to, so we can expand this factor 8 pi nu square upon c cube h nu, and exponential is 1 plus x squared, like this. So we neglecting the higher order terms as nu is very low, so we can write minus, neglecting other higher orders, so we get h nu by kt. So at low frequency we get the Wien's law as this, which is the at low frequency Rayleigh's law can be derived from this Planck's distribution law. So we get that at low frequency the energy density does not depend on the Planck's constant. There is no role of the Planck's constant at low frequency, because the Planck's constant is itself up very low. So there is no role for the Planck's constant. Now Stephen Boltzmann law can also be derived using this expression by integrating over the frequency range d nu. If we integrate this expression, we get the Stephen-Boltzmann law. So this is a complete law of Planck's which determines or which can make understand about the black body radiation. Now we are going to study that in the graph, if we have this energy density here and here frequency, and black body radiation is like this, it has a peak like this. So it is at T equals to 2000 Kelvin. Let's say it is like this. So we see a continuous distribution spectrum. For higher temperature, we observe that there is a shift in the maximum of the frequency as well as the energy density increases. Likewise, at very high temperature, this energy density increases as well as the maximum of the frequency increases. So there we can see that the maximum of the frequency is changing, that is going from the infrared to ultraviolet region. So this is the reason for the change in the color of the body when the temperature changes. So when temperature increases, frequency increases. And we have seen that in the Wien's law and Rayleigh-Jean's law satisfied at lower frequency and diverges at higher frequency. Rayleigh-Jean's law and Wien's law satisfies at higher frequency. This is according to Wien's law. So we have studied here about the black body radiation and Planck's distribution law, and in the next lecture we will discuss about the Wien's displacement law as well as some numerical based problems, and later on the photoelectric effect. Thank you for listening.